Hey, so welcome to this little, I guess, tutorial, little class I want to give on. It's excerpts from the book by Walter Rudin, Principles of Mathematical Analysis. So this is like a basically like a first semester course in real analysis, and chapter 5 is where we start to talk about differentiation. And so I'm just going to do like a few excerpts from this chapter, and then maybe go on to do some from chapter 6 and 7, so forth. So if this is helpful to you, great. I hope that it is. Feel free to, you know the thing, give it a thumbs up, subscribe, what have you. Okay, so the first thing we're going to talk about is called, whoa, that's way too big. Is called, oops, let's see, I gotta go here and here. Yeah, it's the derivative of a real function. So in Rudin's book, he spends a lot of time talking about real numbers and complex numbers. So later on, there's going to be a definition about complex numbers, the derivative of a complex number, derivative of a vector valued function, and so forth. So we have to distinguish between functions that are real valued and functions that are complex. So here is our definition. So what we're going to do, we're going to say let f be defined on some interval, so a closed interval, and actually we need to say and real valued. So it's going to throw that in there because you can't be ambiguous, right? So it's f is defined, it's real valued on a closed interval from a to b. Okay, so then we're going to say for any x in that interval from a to b, we're going to form a quotient. So you probably recognize this as the difference quotient. So we're going to form phi of t, which is equal to f of t minus f of x over t minus x. Okay, so now you're like, hey, wait, where did t come from, right? Okay, so t is also in this interval, but here we have that a is less than t and t is less than b. So t is not going to be equal to the endpoints, and also we want t not to be equal to x. So if you think about what's happening is we're taking the limit of the, well, we haven't taken the limit yet, but right here you've got, like, you might recognize this as your good old-fashioned slope formula. So if I drew a line from x, from the point, let's see, if I drew a line from f of x to f of t, then this would be the slope of that line, right? Okay, so which would also be the average value. So you probably remember that from calculus. So now what we're going to do, because I already told you the secret, we're going to take the limit as t goes to x of phi of t, and we're going to call that f prime of x. So we're letting the limit as t goes to x. We're going to let t go to x, and then, of course, this difference becomes the slope of the tangent line at x. In other words, f prime of x. Okay, so now this only works, of course, provided that this limit exists. So we define the derivative in terms of a limit. And actually, I think what you'll come to find out in, well, I know in calculus, what I've come to believe is that the limit is probably like one of the most important concepts. And then after that, continuity. But anyways, this thing f prime is the derivative of f. Right. And the domain of this function, f prime, the domain of f prime is the set of all x for which our limit exists. Our limit phi of t, right, exists. Right? Because you can't have f prime of x if the limit doesn't exist, since it's defined in terms of a limit. Okay, so when does a limit exist? I'll leave that to you to check out, but you have the left side limit, you have right side limit. And in analysis, we talk about limits in terms of epsilon and delta. So that's back in chapter 4, so I'm going to skip that part. Okay, so there's a theorem now. So here's our theorem. It says that let f be defined on a to b. So f is a function on a to b. And if we can say that f prime of x exists for some x in a to b, then, so if f is defined on this closed interval from a to b, and the derivative exists for some x in the interval, then that means that f is continuous at x. So this is, differentiability implies continuity. Now, of course, the converse obviously isn't true. Maybe it's obvious, maybe it isn't. But let's look at a proof. Okay, so let's look at this derivative. Well, actually, let's think about this for a moment. Here's my derivative, right? This is the limit as t goes to x equal to f prime of x. Now I know this exists because we supposed it here. So f prime of x exists. All right, and f is a function defined on AB. Well, okay. So what does it mean that f is continuous? We have to go back to, we'll just look at, a rudimentary or sort of a naive definition of continuity for the moment. And that definition of continuity is this. So let me just, this is so big. So let me just write down, I'll just say this is a naive definition of continuity. So basically, if f is continuous at x, then what happens? Then the limit as t goes to x for f of t will be equal to f of x. Right. So what does it mean then? If f is differentiable at x, then f is continuous at x. So here's what we're going to do. We're going to say, okay, if f is continuous at x, or I'm sorry, if f is differentiable, then the limit as t goes to x for f of t minus f of x over t minus x is equal to f prime of x. Okay, so we want to show that f is continuous. So we want to show from this that, so if f is continuous, then that means the limit as t goes to x for f of, for f of t is equal to f of x. So in other words, that means that the limit as t goes to x for f of t minus f of x would be equal to 0, right? Because it would be continuous. So as t goes to x, we can write f of t minus f of x. Well, this is equal to, so let me write it like this. F of t minus f of x is equal to f of t minus f of x over t minus x. Now you might be like, what are you talking about? So I really want to show this somehow, right? This is what I have to show. So I'm going to use the limit because, or the definition, the limit definition of the derivative, because I know the derivative exists. So now I'm going to just go like t minus x and t minus, oops, try that again. And t minus x like this. Okay, so on this side, I'm going to get f of t minus f of x is equal to f of t minus f of x over t minus x times t minus x. And remember what we said up here. We said that t was going to x, right? So as t goes to x, what's going to happen here? Well, it's also gigantic. As t goes to x, I have that this one will be the derivative, right? That's the definition of the derivative, right? And as t goes to x here, well, what happens as t goes to x? This becomes 0, right? You get t minus t, so you get times 0. Okay, so we've got it. We've got, now we've got this right here. We've got f of t minus f of x is equal to f prime of x times 0, which gives me f of t minus f of x is equal to 0, which implies, and that's in the limit, right? So that's as t goes to x, right? So as t goes to x. So in other words, the limit as t goes to x for f of t is equal to f of x, which was our definition of continuity. And let's see, we could state it in terms of a metric space, and let's see what then we would say. Well, no, I don't want to get into it because I don't have all the formulas right in front of me. I don't want to write it down wrong. So that's it. So if your function is differentiable, then it is continuous at the point x. So that's all we're saying at that one point, right? So, and of course, obviously, the converse of the statement is not true, right? So we can say this if f is, well, let me just write it like this because it's shorter. If f is, we'll just say it like this, defined on AB, real value, right? And f prime of x exists for some x in this interval, which includes a or b, then does it include a or b? Yeah, has to, because that's the statement. Then f is continuous at x, but f is, so let me write this down. So this is true. We just proved it. True. that f is continuous at x, then maybe f prime of x exists. But it's not guaranteed to. So it does not imply f prime of x exists. It doesn't imply differentiability. And if you want to check that, I recommend you check, look at the function f of x equals the absolute value of x for f prime of 0. And you will see that although this function is continuous at 0, it is not differentiable. Okay, so like I said, this is just like a hodgepodge of, I didn't say the word hodgepodge, but no, I did. This is like some excerpts from this chapter. So I just want to do one proof of one differentiation rule. So there's several rules. You've got your plus or minus. So if you have the f plus g prime acting on x, or f minus g prime acting on x, then that is equal to the sum or difference of these individual derivatives. And also, of course, there's the product rule, which we know it by from calculus, which says that the derivative of f times g acting on x is equal to f prime of x times g of x plus f of x times g prime of x. And you can, because it's addition, it doesn't matter. So it's like the derivative of one times the other, et cetera, et cetera. And then there's the quotient rule. So quotient rule says g of x times f prime of x minus g prime of x times f of x all over g of x squared. Okay, so I just want to prove this one. And actually, this one's like super easy, maybe depending on how much you've studied. And this one are basically the same. So I'm just going to do this one. So let's prove the product rule. Okay, so how can we do it? Well, we need to say, so when you prove things in analysis, you have to you can't leave anything out, right? So we need to say this, let f, we're going to let f and g be, I forgot to write g. Let f and g be defined on this interval from a to b. And we're going to say that they're also differentiable. So they're both differentiable at some x in AB. And anything else? Then no. Okay, so then what we're going to do is, okay, so this is like the preliminary statement. F and G are defined on some closed interval. They're differentiable at some point in the interval. And notice that I included the endpoints here, A and B. Okay, so I'm just pointing that out because sometimes I won't include the endpoints. Okay, so now what we're going to do is we're going to introduce a new function. So we're going to say this. We're going to say let h of t be equal to f of t times g of t. Okay, so now we've assigned this function to be the product of our two differentiable functions on this interval. And where do you think t is at? Well, yeah, t is in AB, right? Okay. So now we're going to say, well, let me just say with t. T is, well, I just got to say it like that. T is also in AB. But I'll say t isn't x. Okay. So then what do we know about h prime of t? Well, h prime of t should be the limit as t goes to x of, oops, not yet. of, let's see, no, slow down. So you got to do it like step by step, right? So let's say, sorry. So it's going to be h of t minus not minus h of x divided by t minus x. All right. So now we're going to replace h with the right-hand side of the equation. Okay. So, I really want to go back and let me just exclude t from being a or b. Okay. Better now. Okay. Yeah. Because x can be a or b, and I want t to approach a or b, and I don't want t actually to be equal to x. Okay. All right. So now let's do the next step here. So I'm going to say, okay, h prime of t is equal to the limit as t goes to x, but h of t is f of t times g of t minus f of x times g of x, all divided by t minus x. Okay, so now this is like, I don't know, it's like the first time you see this, it's kind of like, wow. But I guess people see this trick at different times in their mathematics study career. I guess some people see it in high school because you can use it to solve like trigonometric identities. But anyways, so what we're going to do is we want to create this here. Where's it at? We want to create this, but we don't have enough terms to do it. We don't have the right terms to do it, basically. And this is how you do like proofs in math. Basically, you know what you want to get, and so you try to figure out how to make the thing that you have into that. And one of my professors told me that you follow your nose. So it's kind of like that. Well, this one is just got a standard. This is like a standard proof, right? So really, once you know the trick, it's not really any creativity involved here. But this kind of methodology, this learning this type of thing, like helps you to do other proofs later on. So here's what we're going to do. We're going to add and subtract the same term to get the thing that we want. So here I'm going to write f of t times g of t minus f of t times g of x. And then I'm going to add that same term, f of t plus, so yeah, like this. And then g of x up here. Okay, so what did I do? Nothing really. I just am algebraically manipulating this to get the thing I want. So I just added 0, right? Okay, so now I'm going to take advantage of some limit properties. So the first thing I'm going to do is, actually, I'm just going to factor. So you can see I've got f of t here and f of t there. And then over here, I've got g of x and g of x. And those were the things that I needed, right? So that's why I had to add this, these extra terms. So I'm going to factor out the f of t. And now I have g of t minus g of x here, like this. And then here I'll factor out my g of x. And what's left is the f of t minus f of x. And everything is divided by t minus x. Okay. So now, what is the next step? Well, still we're going to use limit properties. So what I'm going to do is split this into 2. Actually, yeah. So it's kind of like distributing the limit in a sense. And I'm going to do it like several times. I'm just actually going to be like a little, maybe overly detailed, maybe. Okay, and then I'm going to add that to the limit as t goes to x, g of x, f of t minus f of x, all divided by t minus x. Okay, so now I've got 2 limits. Remember, this is one of the properties of limits. The sum of the limits is the limit of the sums. So now I'm going to actually use the product, the rule for the products of limits, and split it up again. So that I've got this and this, right, over t minus x plus the limit as t goes to x of g of x times the limit as t goes to x f of t minus f of x over t minus x. Okay, so now everything that I wanted to get was there. Now, let's go back and make a little note that, note f, we said that f was differentiable. We said both f and g, so actually I'm only worried about f though. So f is differentiable at x, right? So what did we just say earlier? Well, that means that, therefore, f is also continuous at x. So what does that mean? That means that this piece right here, let me just grab a different color. That means that this piece is equal to f of x, right? Since it's continuous. So you may say, well, I already knew that, but it doesn't matter in analysis. You can't just say like, oh, we know that. You have to, you got to do more than that. You got to prove it, right? Okay, so this is continuous. So we get f of x times, now we know what this is, right? F and G are, actually I should write F and G are, okay, so I changed it a little bit, right, whatever. So this now becomes G prime of x. That's the definition of G prime of x. Now this is just a constant really. The limit as t goes to x of G of x, well, there's no t here, so it's just the limit of a constant essentially. And here, this is exactly the definition of f prime of x. So this guy is f prime of x. So h prime of x is equal to this, just like we said in the, well, anyways, h prime of x was, h of x was f of x times g of x. So h prime of x is f times g prime plus g prime times, plus, I'm sorry, f times g prime plus g prime plus, I can't say it for some reason. F times g prime plus g times f prime. Got it. Okay. So there it is. And actually, you know what? I made some mistakes right here. Let me go back and fix those. So actually, you say I wrote a t here. That is wrong. So that should have been an x. My bad. I know I did that earlier today too, because it's the limit as t goes to x. You see, x is stationary and t is moving. Okay, there it is. All right, the next thing I want to tell you about is the way that Rudin defines the chain rule. And it's kind of an interesting, I mean, Rudin has an interesting perspective, and I sometimes criticize him, not that I'm anywhere near his level, but just because it seems like some of the things he does are like less than straightforward. But I think one thing it does is it forces you to get like really familiar with things because you have to keep repeating it. And I don't know if this is by his design or not, but it ends up making you like really explore it more deeply in a sense. And I also like the way that he uses metric spaces as a way to kind of like, I don't know, it puts things in a more abstract basis than using simply the real line in Euclidean space without really defining metrics. Because I've seen analysis books where they don't talk about a metric space. They just use the typical distance, the typical, just the typical distance function and everything in terms of epsilon delta using that distance function. And I like the way that Rudin uses the metric because it kind of puts things on a more abstract level. You can think about, oh, this is true for any metric space that has a distance defined in the way that satisfies the properties of a metric space. So I think I like that. I think that's interesting. But anyways, let me get back to this. So the next theorem is the chain rule. So most of you probably know what the chain rule is if you're watching this. So here it is. Let's look at the theorem. And I'm just going to write the theorem. I'm not going to prove it because the proof is like, not going to lie, the proof is a little difficult and it takes like too many pre-proofs, I guess you would call it. I guess I have to go back and redefine the derivative in a different way. So I don't want to prove it. So, all right, maybe some other video. There is a really good proof. If you go to YouTube and type in real analysis MIT, you won't get a real analysis course from MIT, but what you will get is a guy, I just don't know his name. Maybe I can post a link. And he does a great job of explaining Rudin and analysis. All right, so let's do it. So here we're going to make use of continuity. This is where we really start to make use of continuity in the theorems in analysis now. So suppose f is continuous. And where is f continuous, you might ask? That's right, on A to B. Okay, so f is continuous. F is differentiable at some point x. And of course, well, let me write it like this. F prime of x exists for some x in AB. Okay, so right now we've got f is continuous on AB. F prime of x exists at some point AB. Okay, and now we're going to talk about another function called g. Okay, so f is continuous on the closed interval from A to B. F prime of x exists in the interval. Now we're going to say, now g is defined on some interval. We're going to call it I. That's what Rudin calls it. Some interval I. Now, the thing about I is that I contains the range of f. So so it means like f of x is the input value for g, right? Okay. So I contains the range of f, and furthermore, and g is differentiable at some f of x, which is in I. Okay, so here's our setup. We've got two functions. One's continuous on A to B with the derivative at x in A to B. And then the other function is composed of the former, right? That's why the domain of G is the range of f. Okay, so there we have it. Now we're going to do this thing again where we introduce a new function. So we're going to say we'll say if h of t equals g composed of f of t, and here we're going to let t, of course, t has to be in our interval from A to B. So t is in A to B this time. And now we're going to say then h is also differentiable at x and h prime of x is g of f of x times f prime of x. Okay, so the proof of this is pretty interesting, but you have to go back and like redefine the derivative where you include an error term that like goes to 0 in the limit. Yeah, so that's all I'm going to say about that. So the things I want to point out here about how Rudin defines the chain rule is basically it's in the setup. If you have to like take some exam where you have to talk about the chain rule from Rudin's book, you just need to remember that you've got two functions. One is continuous on the interval. So it's continuous on a closed interval. It has a derivative at some point in this interval, which means like the entire interval anyways. And then there's a second function that has as its domain the range of the previous one. And let's see. And also that function is differentiable at some point. So notice we didn't talk about the continuity of this function g, but we did talk about that it is differentiable at this point f of x, which means that it's continuous at that point too. Okay. So that is the chain rule. And now what I'm going to do is move on to, let's see, what comes next here. I'm going to talk about local maximums and local minimums. Okay, so first, let's just define local maximum. So here's a definition. So again, we're going to deal with a real function. So let f be a real function. And this time we're going to say that it's defined on a metric space. So f is a real function on a metric space. We'll call it x. Typically we would say that. Then we can say that f has a local maximum at some point, let's say at a point, I'll just call it x. Little x in this metric space if there exists a delta greater than 0 such that, now this is where we go back to our epsilon delta days. So f of, let's just say f of y for the heck of it. Where f of y is less than or equal to f of x for all y in the metric space with the metric. So we're going to use the metric on x, right? Because this is our only space. Okay, so when the distance between x and y is less than delta. Okay, so here's our definition of a local maximum. And now what I want to do is change it to be the definition of a local minimum. So I'm just going to make a couple of changes here. So first I'm going to just change this to say minimum. So there's a minimum at this point x in the metric space x if for some delta greater than 0, if there exists some delta greater than 0 such that, now I've got to change the direction here, that f of y is greater than or equal to f of x for every y in our metric space x, with the distance between x and y less than delta. Okay, so that's what it means. Basically, if you want to think about it, like you've got a interval. Here's x. Here is x minus delta. Here's x plus delta. And whenever y gets in here, then f of x is either the largest or the smallest. So local maximum, local minimum. Okay, so let's use this to talk about another theorem. So here's my theorem. So we're going to say this, let f be defined on the closed interval from a to b. Right. Then we can say if f has a local minimum, and actually this works for the maximum too, but I'm just going to do the minimum. Local minimum at a point x. Hey, that does not look like an x. So f has a local minimum at a point x in the closed, what am I saying, open interval from a to b. And if our function is differentiable at that point, then f prime of x equals 0. Okay, so we've got, what do we have here? We've got two things going for us. We have to have two conditions present, in other words, so we need f to be defined on a to b. And we need to have a local minimum. Okay, so f has a local minimum. So actually I lied, there are three conditions. And we need f prime of x to exist. So if these three things happen, 1, 2, 3, then this thing should happen here. The derivative at that point at the local minimum should be 0. So let's prove it. Okay, so here's the proof. So remember that what makes the local minimum is that we have this little interval. So first we know that f is defined on a to b, right? F is defined on a to b. Maybe I should make it smaller again. Smaller. F is defined on a to b. And what else? F has, I'm just going to repeat, because if you don't, then the magical guardians of mathematics won't come to bless this proof. So like, you know, a lot of times if you're doing this like for academic, for like a grade, you can think of these things as a magical incantation. But actually it's not. You're just like saying what has to happen in order for this conclusion to logically be reached. Okay, so let f is, that doesn't make sense. Oops. Let f be defined on the closed interval from a to b. F has a local max at x in ab. And we're going to say, you know, f prime of x exists. Okay, so these are all of the things. We want to show that f prime of x equals 0. So what did we say before? We said that in order for there to be a local, oh wait, I want to do this for the minimum, sorry. In order for there to be a local minimum, we have some little, I'm going to call it a neighborhood. We had some delta neighborhood around the x that whenever some point got close to it, the f of that point was larger than f of x, right? So we've got this interval here. So let's say let delta be greater than 0 and put, so we're going to put delta in this interval, but we're going to do it like this. A will be less than delta. Oh, wait, not delta. Actually, I'm going to write it like this. This left side is x minus delta. And then x is going to be in the middle. And then, of course, x plus delta is on the right side of x. and this is less than b. Okay, so now I've got this little delta neighborhood around x, right? Okay, now what I'm going to do is we're going to say, suppose we've got a t now. We've got a t. We're going to put t in this little neighborhood between x minus delta and x, right? So t is greater than x minus delta and less than x. So then, if you look at this quotient, so remember the derivative, right? F prime of x. But first, let's just look at this quotient, f of t minus f of x divided by t minus x. Okay, so what we want to do is just like analyze this for a moment and think about what we've got here. We know that f of x is the, what is this guy? This is the local minimum, right? So this is my local minimum. So that means that f of t here, f of t is larger than f of x. F of t is bigger than f of x, right? Because that's the definition of a local minimum, and actually it can be equal to. So f of t is greater than or equal to f of x. Now, what about t and x? Well, we know that t is less than x because that's what we assumed here. Okay, so let me just say this. F of t minus f of x, this is greater than or equal to 0. What about t minus x down here? Well, t is smaller than x, right? So that means that this is less than or equal to 0. So that means my whole quotient here is negative, yeah? Less than or equal to 0. And so if I take the limit, so I'm going to take the limit then as t goes to x for f of t minus f of x over t minus x. And what do I get? I get something that's less than 0. This thing is negative. Okay, so that's part one, basically. We'll say this is equation 1. Now we're going to look at the other side. We're going to say let t be a new t, or it could be the same, I don't know, the different t. I'm just going to use t again. I don't care. So now we're going to say choose some t in this interval from x to x plus delta. Okay, so in this case, t is larger than x, but it's less than x plus delta. Okay, so it's still in the delta neighborhood, which means that our f of t will be larger than f of x because of the fact that f of x is a minimum, right? So let's examine it again before I take the limit. Let's just be a little methodical here. So I don't like that color. It's kind of bright. So I'm going to do f of t minus f of x again, divided by t minus x. Okay, so now this numerator is still positive because f of t is larger than, f of t is larger than f of x, since f of x is our local minimum. But this time, t is larger than x also. So that means these are both greater than or equal to 0. All right, so that means that the limit as t goes to x for f of t minus f of x over t minus x is greater than or equal to 0. Right? So, okay, so what did we just show? Let me just say it like this. So looking at 1 and looking at 2. So this is, you know, f prime of x. And this is also f prime of x, right? So what do we get? We get that, okay, we'll just do it like this. So by equation 1, f prime of x is less than or equal to 0. And by equation 2, f prime of x is greater than or equal to 0. So what does that mean? Well, since they're both true, that must mean that f prime of x is equal to 0. And so we have it there. So if we have the condition that f is defined, so f is defined on a real, it's a real function, f is defined on closed interval from a to b. So I'm just going to assume it's a real valued function. Okay, how about that? Real valued, although I didn't write it down to begin with. So f is defined on this closed interval from a to b. F has a local minimum at f of x, and f prime of x exists, then that means f prime of x equals 0. So you can use exactly the same, well, yeah, basically exactly the same proof to show that this also is true if you have a local max. And if you remember calculus, which you probably do, this might remind you of Fermat's theorem, because it is that in many calculus books, or at least in James Stewart calculus book, which is the one I use, which is the one I love. Yeah. Okay. So let's see. I want to do like 2 more things, I think. Yeah, let's do 2 more things. So the next thing I'm going to do is a theorem that I'm not going to prove. Sorry. But I want to just write it down because I'm going to use it to prove another theorem. So here's my theorem. It's called the Cauchy, or Koshy, however you want to say it, Cauchy Mean Value Theorem. And I'm not 100% certain, but this might also be called the Generalized Mean Value Theorem. I can't remember that. Okay, so what does this thing say? Well, let's take a look. So we start with 2 functions. We've got f and we've got g. And these guys are continuous. Now this is important. They have to be continuous. They're continuous and they're real and they're functions. And where are they continuous and real? You guessed it, on a to b. Okay, so, and they're also differentiable. So f and g are continuous, real functions on a to b, and we're going to say differentiable on the open interval. So here we want to exclude derivatives at the endpoints. Okay. So then, so these are our conditions. We've got 2 functions, f and g. They're continuous real functions on the closed interval from a to b, and they're differentiable on that entire interval except the endpoints. Right. So then our conclusion is going to be, then there's some x in this open interval, okay, not at the endpoints. There's some x in here at which we get this result. If I take f of b minus f of a times g prime of x, this will be equal to g of b minus g of a times f prime of x. Okay, so I don't really want to prove that, but I do want to use it to prove the next thing I'm going to prove, which is just the regular mean value theorem. Okay, so the proof of it, it's not incredibly difficult. So I recommend you look into it. And I'm not going to though. And actually, there's another proof of this that's like a visual proof of this is pretty satisfying. So you might check into that. All right, so now I'm going to use that to prove the mean value theorem. So just the, I guess you call it the, I don't know what you would call it. I'm just going to call it the mean value theorem. So theorem, the mean value theorem. Sorry about my handwriting. the mean value theorem. So again, we have the same initial conditions, except this time we're only talking about one function. So we're going to say if f, so this is like the same theorem you're used to in calculus. If f is continuous on closed interval from a to b, and it's differentiable on our open interval on the open interval from a to b, then, so these are our two conditions, very simple. F is continuous on the closed interval from a to b, f is differentiable on the open interval from a to b. Then the conclusion is that, and you probably know what it is, then we get that, there's a lot of different ways to write it, but basically we're saying that the slope of the secant line is equal to the value of the derivative at that x. Oh, you know what? I forgot to write. Then there exists an x in a b such that this is true. Okay, and so generally, well, at least in Rudin's book, he just goes ahead and writes it like this because it's actually quite similar to the Cauchy Mean value theorem. Okay, so here's what we have, and now we're going to prove it. And the proof is fairly simple, straightforward, because we can use that previous, what you might call it, Cauchy Mean value theorem. Okay, so we're going to say let f be a real valued function. I'm just going to include everything, right? Don't leave anything left to the grader to guess, right? So if I'm doing this for a test, right, I'm going to write down all the details. Let f be a real valued function on this closed interval. Wait. Real valued. This is pretty important, so I'm just going to put it here. Real valued continuous function on a to b that is differentiable on the open interval from a to b. And actually, let me just throw in g here. So we're going to say let g and f functions. So you're like, what's this about? Well, I'll show you. So f is a real valued function, g is a real valued function. They're continuous on a closed interval, and they are differentiable on a to b. So now I'm going to say let g of x equal x. Okay, so then it seems like a kind of a fake proof. It's not, but it kind of seems like it. Then by the Cauchy mean value theorem. And now if this were like a class, I would prove the Cauchy mean value theorem also, because like, how can you write down a proof and use it to prove another proof if you haven't proved the first one? Or how can you write down a theorem and use it to prove another proof if you haven't proved the theorem? So that's kind of, that's not good, but this is just like a casual sort of tutorial, so I don't mind it. So then by the Cauchy mean value theorem, we have f of b minus f of a times g prime of x is equal to g of b minus g of a times f prime of x. And now let's look at what g is. Well, g of x is equal to x, which means that g prime of x is equal to 1. And it also means that g of a is equal to a, and g of b is equal to b. So we can write this down again. We get f of b minus f of a times g prime of x, which is just 1, is equal to g of b, which is b, minus g of a, which is a, times f prime of x. Okay, so yeah, I kind of feel like I should have proved the first one, but okay. I don't really have to for this class I'm taking. So I'm just doing this. So f of b minus f of a is equal to b minus a times f prime of x. And there you have it. Okay. This one's pretty easy to visualize. Got some function here. It's continuous on a to b. There's a, there's b. So I have a secant line going from a to b. There it is. And actually this f of b minus f of a over b minus a represents the slope of this line. And so what it says is there's a, well, I guess that's big enough, fine. There's some point here where the tangent line has the same slope. Bam. Right, so they're parallel slopes at this point here. Just like that. Okay. All right. Let's see. Now, I kind of want to do some more things, but I don't know if I want to do it now. I want to talk about, maybe next time I'll talk about L'Hopital's rule. S depends on what area you're from, if you want to include the S or not. Then I want to talk about higher order derivatives. And then the Taylor series. Now the Taylor series is basically, in a real way, it is an extension of the mean value theorem. It's like the mean value theorem is well, it's the slope of a tangent line. Basically, it's like, yeah, the mean value theorem is like the Taylor series for, it's like one of the first couple terms of the Taylor series. I'll just leave it at that. But they're very related. And actually, the mean value theorem is crucial to proving needed to prove this, which we'll talk about. So it's actually, is it Taylor series? Or is it, no, it's not the Taylor series. Sorry. I'm talking about the polynomial approximation. So like, in a sense, Taylor series or Taylor theorem, that's probably better. Taylor's theorem is a better way to think of it. It does use the Taylor series coefficients to create polynomials, et cetera, et cetera. Okay. Now, in order to talk about L'Hopital's rule, we're going to have to talk about something called the intermediate value theorem for derivatives. Intermediate value theorem for f primes. And then higher order derivatives, not too difficult. It's just like the derivative of the derivative of the derivative of the derivative if it's differentiable. Yeah, okay. So next time we'll start here with, actually the next time I'm going to talk about how to use the mean value theorem to prove a lot of stuff. Actually, we're going to start by proving, to prove that, to prove a function is increasing, decreasing, or constant. And then from there, we'll talk about the IVT for f prime, then L'Hopital's, and then higher order derivatives, which will lead us directly to Taylor's theorem. And then I'll spend a little bit of time talking about complex and vector valued derivatives. And then we'll go on to chapter 6, which is about integration. Okay. Well, thanks for watching. If you watched this far, I appreciate it. Hopefully this helps you.